Everybody, please take your seats. Take your seats quickly or I might... No. Hi, how are you?
Good, how are you doing? Yeah. That's it.
All right, if we could settle the room, please. Thank you all for joining us for session 4, which is the first exoplanet session of the JWST conference. My name is Susan Mullally. I will be your chair. And up first, we have Elizabeth Matthews. And go ahead.
How's that? Yeah, okay, perfect. Thank you so much for having me. Sorry about the technical difficulties. And thank you so much to the SOC for inviting me to tell you a little bit about some of the exoplanet work that I'm excited about with JWST. This isn't working. Do it over here. No, I can't do it over here either. I'm sorry. You said the spacebar would work? We can try that as well.
Now it'll work. You just had to get started.
Okay, cool. Let's try again. So I'm going to try and convince you today that not only is JWST an excellent exoplanet characterization tool, there's also some really interesting space to do exoplanet discovery work as well, and also some kind of in-between work where we look at systems where we think there's a radial velocity planet, but we can maybe also image that planet for the first time. So on the characterization side, I think we've already seen a bunch of really exciting press. This is just some of the figures that I grabbed from some of the most exciting press releases, including a couple of the ERS results, which I think you'll hear a lot about in the next talk. And of course, we've also seen these really exciting pictures of the solar system planets. But one thing that I wanted to highlight was that the solar system planets are actually quite different to any of the planets that we look at when we study exoplanets. So this is how those 4 gas and ice giants compare to the population of known exoplanets. And you can see especially the radial velocity and transit planets are very much close to their stars, and the directly imaged planets are very massive, so bigger than any of the solar system giants, and also very young, so much quite different to the solar system planets in that direction as well. So this is a plot where I've taken the classic diagram of all of the exoplanets, and I've color-coded them by age. And you can see the directly imaged planets, which I've marked with stars, really jump out as a very different population than the radial velocity and the transit planets that we know about. These are much, much younger systems than the bulk of radial velocity and transiting planets. And the reason for that is that planets and brown dwarfs get cooler and colder throughout their lifetimes. So they form, they have a lot of energy left over from formation, and then they slowly cool and contract and become lower luminosity. And because they're colder, they also move more of that emission into the mid-infrared. So if you look at a star that's very young to search for planets, you have a much smaller difference in brightness between the star and the planet than if you look at a solar system age planet, where you're looking at a really heavy contrast barrier between the brightness of the star and the brightness of the planet that you're trying to find around it. So especially from the ground, we've been very much limited to the youngest and most luminous planets in terms of direct imaging detection. And with JWST, we also started with some of these easiest to do, youngest and most massive giant exoplanets. So I want to just very briefly talk about a couple of the results from the JWST ERS program that was focused on direct imaging, which was led by Sasha Hinckley, who you'll be hearing from in a lot more detail, I think, in the next talk. But one of the results from this program that I was particularly excited about was the first images of HIP 65426b with JWST. So this is a planet that was first detected from the ground using the SPHERE instrument. It's about a 16 million-year-old planet. And you can see that planet signal pops out really clearly across the NIRCam and also the MIRI wavelengths. So in each case here, the star is roughly the position of this star, which has been annotated on. And almost all of the starlight has actually been removed during our post-processing, leaving just the signal of that planet, which pops out super clearly. And you can see the quite complex PSF that we're dealing with this analysis as well. You can, of course, also put those points on an SED. So here I'm showing you in black all of the existing data, so all of the ground-based data for this system. And then with orange, the JWST points that we detected across the NIRCam, and then also the 2 MIRI points as well. These are the first 2 exoplanet images of any exoplanet beyond 5 microns. And they're really helpful in terms of constraining the bolometric luminosity of this planet really precisely, because you really get to model the full SED much better than we ever have before. But the thing that I was most excited about with this result from the ERS program was actually to see the performance of JWST, to see that JWST is working extremely well for direct imaging. So this plot here shows a bunch of different reduction choices and then shows in black the actual performance that we got with the instrument, and then in blue the pre-flight predictions of what we might be able to expect. And you can see for each of these different reduction choices that we're consistently doing better with the actual data than we were with the pre-flight simulations. So that's a really promising sign for some of the direct imaging work that we'd like to do. For those of you that don't think in contrast and separation, I can also convert these plots into mass and semi-major axis. So this is another plot from Aaron Carter's paper, where you can now see physical units, so the mass and the true separation rather than the projected separation. And this has been converted here into a completeness curve. So each of these contours is indicating the fractional likelihood of detecting a planet at that specific mass and semi-major axis. So you're also folding in the geometry here, the fact that some of these planets, especially very near the contrast curve, will be hidden behind or in front of the star some of the time. So far I've talked a little bit about some of the direct imaging, and we know that the telescope is working really well for direct imaging. But one of the things that we would really be able to do, would be to combine direct and indirect image techniques. So rather than having to go and find these planets where we're typically restricted to the very young planets, to perhaps also be able to directly image systems where we know about a planet indirectly, where we know about a planet based on the acceleration of the host star. And there's a number of reasons that we'd like to do that. The first is that this allows us precise dynamical mass measurements, and it gives us 3D orbit constraints. So especially if you have a long baseline of radial velocity data, and then also an image, you have really good information about the orbit of the planet, for example, whether it's eccentric, which can help point to the formation and migration pathways of some of these things. So whether they're, for example, migrating through the disk, or whether they're migrating much more dramatically through dynamic scattering, which might leave a much higher eccentricity on any planets that are detected that way. Another really important part of this is that we can then test theoretical models of planet formation using those dynamically measured masses. So these models of planet formation, like those cooling curves that I showed you at the very beginning, are an absolutely crucial part of so much of the work that we do interpreting our direct imaging surveys. We typically assume that we can convert the luminosities into masses, and then we can use those masses to calculate occurrence rates, detection rates, and use those compared to, for example, the radial velocity population. But that relies on those models being correct. And at least on the brown dwarf side, I don't think that is as clear-cut as we might hope it was. So this is a plot from Mirek Brandt, which shows all of the brown dwarfs which have really good dynamical mass measurements and also really good luminosity measurements. And they're color-coded. So the green ones, the luminosity and the mass agree. The yellow ones are brighter than we would expect based on their masses. And the light blue ones over here are fainter than we would expect based on their masses. Now, I think this is a problem. There are still not so many points on this plot, so I think there's still some uncertainty as to exactly what's going on. In particular, there are proposals for both GJ229P and HD4113C that perhaps that object is actually a brown dwarf binary, and that's why it's so much fainter than we expected. But I think it's very interesting that those underluminous objects are all in roughly the same part of the parameter space, and we really need to try and figure this out in more detail. We really need to understand whether this is actually an isochrone problem, which would have implications much more broadly for all of our interpretation of direct imaging surveys, or whether it is actually just that we happen to have found a couple of really weird objects as the first few objects that we found up here in this plot. The final advantage, of course, of combining direct and indirect detection techniques is that it tells us where to look. If we know that there's a radial velocity planet and we think we can detect it, we can image much more deeply than we might be able to justify in a completely unguided survey, because we can really justify spending the time to pick up the photons and potentially detect companions that we just wouldn't be able to get to in an unguided survey where the time limits might be much more constraining. I'm going to go slightly off-piste for a JWST conference and show you a little bit of ground-based data, because I really want to convince you that we understand how to do this and how this works. So this is just one example of an object where we have long-term data, and you can see a really clear orbit here. You can see we have about 3/4 of that orbit covered. And we thought this object might be a brown dwarf based on the radial velocity data. So we collected sphere images of this object as part of a paper led by Emily Rickman, and you can see we actually detected a companion, in this case a low-mass star rather than a brown dwarf, because the system is relatively face-on, so it's relatively massive for the radial velocity signal that we're seeing. Now, one really exciting new dimension that we can use for some of this work is the combination of Hipparcos and Gaia astrometry. And that's really important because that gives us plane of sky constraints, whereas the radial velocity information is giving us line of sight constraints. But by combining those, we can avoid this situation where we think something might be a brown dwarf and it turns out to be actually a star. Because if it was a star, we would have detected it with the Hipparcos and the Gaia acceleration. So the way that that works is that even with just the proper motion measurements from Hipparcos and Gaia, we can see what's called the proper motion anomaly. This is a nice figure from Pierre Cavella that illustrates this effect. So the barycenter of the system moves completely smoothly across the sky. But if you have a star that's actually on an orbit because there's some unseen companion further out, there will be some small additional motion on top of that long-term average proper motion. So you'll see a small anomaly between the instantaneous motion at the Hipparcos era and the instantaneous motion at the Gaia era relative to the long-term average proper motion that we can detect from the change in position of the target. And this works really well, especially when we combine it with that radial velocity information. So this is more of the data. This object here is the one that I just showed you a couple of slides ago from Emily's paper. And for this paper, we actually had 6 objects where we had long-term radial velocity data, and we modeled the radial velocity and the acceleration data. And in each case here, the contours show you where we expect the object to be from that indirect approach, and then the gray stars show you where we actually found these objects, which very much agree with the places that we expected to find these companions. Now, these are all low-mass stars because we did this work from the ground, and we just don't have the sensitivity to push to brown dwarf planets from the ground. And these are all objects where we have relatively good, so relatively clear, well-curved radial velocity trends. But even when we just have a linear radial velocity trend, so you can see this is much less well-constrained, we can still do some of this work, especially if we know, for example, from archival imaging, in this case from NACO, that a massive companion wasn't detected. So in this case, we know from the radial velocities that there's something there. It's extremely degenerate in mass and period, but we can use the archival imaging to rule out some of the most massive companions. We can go back and image it with SPHERE. Oh, sorry, I forgot the slide. We can predict where the companion should be based on the radial velocities and also the Hipparcos and Gaia astrometry. And then we can image it with SPHERE, and you see a source that pops out exactly where we predicted it might be. Again, a relatively massive source. In this case, we think it might be a white dwarf because we just don't have the sensitivity to dig all the way down to planets. I want to show you one more example, and then we'll move on to JWST data. So this is a very long-term RV trend again, and this is what the data looks like in this case. And the contours here show where we expected that companion to be. Here you can see one of the big problems that we're often faced with in direct imaging, which is that there are actually quite a lot of PSFs in this image. And I don't think you need a degree in planetary dynamics to know that these are not all stable planets orbiting around this star. These would not all be able to sit on that same orbit together. And in fact, the problem here is that most of these are background contaminants. And from the ground, the typical contaminants are background stars, but from JWST, those contaminants will start to be much redder objects, so typically background galaxies that just happen to be in the field of view where we're looking. And I want you to bear that in mind for the rest of the talk as well. So I've shown you that we can do this work from the ground. We can predict where the brown dwarfs and the stellar companions might be, and then we can go and recover those with observations. But what about the planets? And the difficulty with the planets is that the radial velocity targets are all older systems, and the directly imaged planets are all younger systems because those are the only ones that are bright enough that they're doable. And it is actually the brightness rather than the separation that's the limiting factor here. So this is a plot where I'm showing, I've zoomed in just on kind of the outer edge of that plot that we had before. And I'm showing in blue some of the planets that have been imaged and in red some of the radial velocity planets. And you can see that there is some overlap here. I've scaled this to be in terms of units of projected separation on the sky, so the semi-major axis, but scaled by the distance. And there is some overlap in terms of where we're finding some of these RV planets and where we're finding some of the imaged planets. But from the ground, these planets were just too faint to directly detect. I've also overlaid the inner working angle and the different thresholds based on the performance relative to the background performance of the various coronagraphs that we have access to. And you can see that for a lot of the RV planets, they're either really on the boundary of what's possible or within the inner working angle and therefore inaccessible. But for a few of them, they're sufficiently widely separated that we might be able to resolve them as long as we can dig down to the sensitivities that we need to be able to directly detect some of these objects. And this RV planet in particular really sticks out as being very widely separated and potentially very compelling for direct imaging, because with JWST, we actually do have the sensitivity to dig down to those colder, older planets. This is an object called EPS-INDI AB, and this is what the radial velocity data looks like. So you can see this long-term trend, and then we also have the inversion, which helps to place much tighter constraints on where the planet should be. And there's also some nice work that's been done by Fabo Feng as well as Florian Filippo, combining this RV trend with the Hipparcos-Gaia acceleration. And we have a fairly clear prediction of where the object should be. This is the 1 sigma contour, so you can see it's not completely wrapped up, but it's relatively well constrained where we think this companion should be. Florian Filippo has kind of a similar prediction. Again, the companion is kind of down in this corner of the observations. And I just want to highlight that this is a super exciting system more generally. This is an extremely nearby star. It's only about 3.5 parsecs away, which is part of why you have that really promising separation between the star and the planet. It has this massive planet that's been detected with radial velocities, and it's also co-moving with a brown dwarf binary, so with 2 70 to 75 Jupiter mass objects. So it's a really ideal laboratory right in our backyard for studying formation, and it poses interesting questions such as why one of the pairs of objects in this system is a almost equal mass binary, and one of them has a much stronger mass ratio, and whether all of these atmospheres and all of these luminosities of these 3 objects are consistent with each other at the assumed age of the system. This is about a 4 gig-year-old system, so it's about solar system age, and we would expect the planets to be around about solar system temperatures as well. So we were pretty excited by this system, as you might be able to tell, so we decided to go and observe it with JWST, with MIRI. We had to wait until, this was a cycle 1 program, but was technically observed in cycle 2, so we had a really long wait while some of you were getting all of your super exciting data. But we do now have the data. It's still extremely fresh, so we're still doing some work to understand exactly what we're seeing in the data. So for the next couple of slides, please take everything with a large grain of salt. But this is what the data looks like. So this is our reduced image of our MIRI coronagraphic imaging of EPS-INDI. And I've just left these predictions up on the side for you as well. And I've gone ahead and circled some green points for you. This one down here is the closest one to where we expected the planet to be. It's not exactly in the right location. We expected the planet to be a bit more over here, so a bit more to the kind of angled separation. This is about 2 sigma away from the prediction from Fabo's orbit fitting with the radial velocities and the astrometry, which is super frustrating because it puts it right on the coronagraph boundary. So the coronagraphs have this kind of cross shape, and if you're on that cross, you have a lot more noise from the star and a lot less throughput, which is kind of frustrating, but I think it's still certainly a promising source, and we're doing some more work to try and differentiate whether this really is a companion or whether this is a speckle, so any leftover stellar noise that we haven't been able to remove correctly in our processing. There's something else up there as well, which is really intriguing. We don't yet know what this is. The 2 obvious scenarios would be either that it's a second planet in the system or that it's a background object of some sort. So I would really like those of you that don't do exoplanets to tell the exoplanet community more about what kind of background objects we might be able to expect. And in particular, I'd really like to be able to work out whether the 10 to 15 micron color of this object is consistent with a planet or with background objects, and how common those background objects might be, so that we can work out probabilistically whether this is more likely to be a background or whether it's more likely to be a true planet. Of course, the slam dunk is to go back and get another epoch and to see whether this is moving across the sky with the foreground star, which actually moves relatively rapidly across the sky, or whether it's completely stationary relative to the foreground star, which would imply that it's a background object, something extragalactic that's not moving. This over here is probably a background that's kind of faint and it's much further away from the star, so we're not so excited about that one. But I think there are 2 compelling sources in this system, although we need a lot more work to really understand whether these are real solar age planets or whether they are contaminants either from the stellar light or from background objects as well. I just want to highlight also that there are a couple of other potentially exciting targets for this kind of work. In particular, there's a Cycle 2 program that's being led by Daniela Bardelez-Gagliuffi and William Balmer, which is going to try and do the second most compelling planet. I think EPS-INDI is the most compelling planet for this kind of work, but 14Her is a really good candidate as well. And this is an intriguing system because it's actually a 2-planet system. So this is what we expect the data to look like if everything works and if the planet kind of meets our luminosity expectations and if it's on the younger end of the age distribution that we expect for this target. And if we do make that detection, we'll also be able to look at the inclination. We should get a much better inclination constraint for the planet that we're able to access with the RV and the acceleration alone. And that will allow us to look at the dynamics of this system and potentially try and study whether the 2 planets in this system have scattered relative to each other as well. Apart from that, it starts to get really tough because we run out of radial velocity planets. But I hope I've convinced you that there's also an interesting angle to go down in terms of looking at objects where we have radial velocity trends, where we see long-term acceleration, but where we don't yet have good constraints on where the planet is or what mass the planet is, and because it's still degenerate with period. But with enough ancillary information, we can still design programs which have a very high likelihood of detecting new planets based on some of that indirect information. Of course, if you don't have any indirect information, another line of inquiry that you can use is to look at other indications in the system that there might be sculpting happening. In particular, we're also really interested in debris disk systems. So this is one example of a debris disk system where the star is kind of in the center here, and you can see the ring of dust, which is somewhat eccentric and relatively narrow in this case. And both of those things imply the presence of a planet that's helping to sculpt the belt of dust. And one of the big open questions in terms of debris disks is actually how much mass there is in this belt, because we're only observing the very small grains. So we're observing the dust, and we don't know how many Pluto-like objects there are, which might be generating all of that small dust. But we think that the mass of those Pluto-like objects in this belt is probably correlated with the mass of whatever planet is internal and is sculpting this belt. So Tim Pierce has this nice model where you have an inner planet, and then you have the disk, and that if there's enough mass in the disk relative to the mass of the disk is able to stay this very narrow belt. But if the planet is much more massive than the disk, then the disk will become destroyed by the influence of that sculpting planet. So the idea here is that the planet and the disk should be correlated in terms of their mass. So we can use these systems to not only try and find that planet, but also potentially learn more about the disk itself, learn about the mass of material that's present in the disk, and maybe even constrain the number of Pluto, not the number, but the amount of material that's in Pluto-like objects in this disk. We have a program to do that in Cycle 2, which is being led by Tim Pierce, which is going to be really exciting. And there are other disk systems where we might be able to pinpoint that the planets should be there sculpting the system, and then potentially go back and observe those planets directly as well with JWST. I just wanted to take the last couple of minutes to also convince you that there is space to do completely unguided surveys as well. You have to be much more careful in terms of your target selection for this kind of work. The imaging is really promising in terms of actually detecting planets, because we can even with a single image, we can potentially try and get planet constraints out as well. So this is a plot from a proposal led by Aaron Carter, which was also awarded time. This is a proposal which is looking at a specific moving group. So for direct imaging, you really want to compromise between the distance. You want stuff as close as possible so that you get the best resolution. But you also want stuff that's as young as possible if you're doing an unguided survey, so that you can really dig down to the deepest planet masses. So TW Hydra provides kind of the ideal compromise between these two factors that are both really important for the direct imaging. So Aaron's leading this program, which is going to go and image a number of these objects in TW Hydra, and we expect to get planet completeness rates something like this. So you can see we actually dig all the way down to sub-Jupiter and even Saturn mass planets with relatively high completeness at the most massive separations. And that's really important because this is truly the only way, JWST is the only option to try and find planets or to place occurrence rate limits in this part of the plot, which actually has been used just as the legend of this plot because there's just nothing there right now. But JWST will allow us to dig down and see whether Saturn mass planets are as rare as the super Jupiter planets that we're currently able to observe at the wide separations. So with that, I will wrap up and just share my conclusion slide. So I hope I've convinced you that JWST is really exciting for exoplanet characterization, but there's also this really interesting discovery space. I've tried to show you that indirect and direct exoplanet techniques are beginning to overlap, and that we're beginning to have the ability to actually target our imaging observations at systems where we think we already know there's a planet there. I also showed you some of the candidate companions that we've detected around Epsilon Indi A. We obviously have a lot more work to do there, but I think there's some really exciting data, and it's going to be a really fun project to work on. And finally, I think we can continue to use some of this sculpting, some of these indirect hints, such as the long-term trends, and then also the disk sculpting, to try and target our direct imaging observations. And there's so much more really good exoplanet science to come. I think we're really just getting started. Thank you very much. I'll take any questions.
Thank you. We have actually lots of time for questions. So I'll take the first one over here. Just be sure to state your name. And
Hi, Laura Flagg. Great talk. For Epsilon Indy, the one candidate that's position was, 2 sigma off. Is the other candidate in a potential position that it could have skewed the RV curves so that you misestimated where the position is, or is it just in totally the wrong place to do that?
This is one of the questions on my to-do list that we haven't had a chance to answer yet, but my favorite theory for the system would be that perhaps this is biasing our fit a little bit and making our estimates slightly wrong for that system. But I think there's a lot more work to do before we try and claim that as the correct answer to this system.
Thank you.
look, do we have any online? No. Any other? Oh, there's one over there.
Great talk. For disks like HD 53143, would the presence of something like a inner misaligned disk, such as has been hypothesized for that particular disk, also place any additional constraints on where planets might or might not be stable for these sorts of orbits and sizes?
I don't know about the inner disk in that system. I would love to talk to you about that more. Tim Pierce is the one that does all the dynamical models. I just did like the observational side of that program. Certainly inner disks are also useful. I think I don't know what the separation of the inner disk is, but I think in a lot of the systems that have both inner and outer disk, the gap between those disks is very large. So you could have a planet that's sculpting the outer disk that doesn't really have much impact on the inner disk as well. But it's certainly something that we should look at in more detail.
Thank you.
All right. Are there any other questions in the room? Oh, let's start.
There's one.
Oh, there we are. No.
This is just more a pragmatic question, and maybe you mentioned this at the beginning of your talk, but is there anything that can be done about the artifacts in the images on each side of the exoplanet to kind of,
Like the shape
yeah,
of the
exactly,
PSF?
the wings, those things, yeah.
Not directly, although for the public image release, they did the best they could to kind of minimize the amount of flux that you could see in those wings to make it a little bit clearer what was going on. But I will say that when we model these systems, we inject copies of the PSF, so we can do a good job of handling that in some of the post-processing to make sure that we really understand the photometry and the astrometry of the companions correctly. But we can't just get rid of the PSF shape, no.
Okay, there's a clear challenge for young image processors because we do this in radio interferometry all the time. We can correct the point spread functions and all that. If we could do that in these images, it would be awesome. Thank you.
You mean like deconvolving
Yes,
with a PSF?
yes.
Yeah. Yeah, it's a good point. I mean, it's not something that we've ever done in the direct imaging community, but it might help to communicate some of these results as well to make the true point source clearer. Because it does come up as a question as well, like, oh, is that a disk around the planet? No, definitely not.
Oh, sure. Thanks for making me get my exercise.
Really
That's all right. I'll make it. Here you go, Marshall.
Just to comment on the last question, postdoc Kellen Lawson at Goddard is doing some great work with deconvolving NIRCam and myricoronography.
Yeah, it's especially important for the disk targets, I think, to try and do the...
Okay, I think we better thank Elizabeth again and move on. Thank you. Right. Right. Up next, we have an online talk by Sasha Hinckley. Sasha, are you there?
Yeah, can you hear me, Susan?
I can hear you. I'm going to stop sharing my screen and hope that you can share yours.
Okay.
Then I'm probably... Do you share the screen? Oh, there it is. Now, if I just put this in... Okay. So you're good there? All right. So, and you're
Sorry, can you hear me and see me okay? And my slides?
Sasha, I can hear you, I can see you, and we see your slides. So Sasha Hinckley is our next speaker. Go ahead.
Great. Thank you, Susan. I'm sorry that I couldn't be there with you today. I'm here in the UK right now. It's 9 o'clock at night. I'm in my office. And for those of you that don't know me, I'm Sasha Hinckley. I'm an associate professor at the University of Exeter in the UK. I'm also the PI for the JWST Early Release Science Program for the direct imaging and spectroscopy of exoplanetary systems, and that's what I'm going to tell you about here. But I think that this is probably a little bit of a diverse audience, and I want to really explain the problem that we face in this. Liz did a really good job in the last few minutes of getting you started on this, but I really want to emphasize a couple of things. In the exoplanet direct imaging game, really what we're trying to do is spatially separate the light of a very faint exoplanet from the glare of its very bright host star. And typically the angular scales we're talking about here are an arc second or less. And the planets we're talking about are typically 4 to 5 to 6 orders of magnitude fainter than their host star. But if we can model all of this residual scattered starlight here, these are our limiting systematics. In the transit community, you have your own limiting systematics, but these are our limiting systematics that we need to model and subtract. And when we do that, we can actually sometimes uncover the presence of bright, self-luminous, Jupiter mass type planets. So here's the object HIP 65426 that Liz mentioned a few minutes ago. And in this game, we're really sensitive to the outer architectures, tens, hundreds of astronomical units. And the real advantage of collecting photons directly from the atmospheres of these planets is that we're sensitive to direct characterization through things like spectroscopy. And this gives things like direct atmospheric abundances that we can measure, and that leads to all kinds of interesting questions. But it's technically very challenging, and we had to face these same challenges with JWST. So I want to tell you a little bit more about that. But before I do that, I want to talk about what I like to think are some of the key goals and challenges of exoplanet direct imaging. And I boiled them down, so forgive me for those of you that are commenting on the things I may have forgotten. The first thing we really want to do is we want to characterize planets over their full luminous range. So far, we've really only characterized planets from about 1 to 2 microns using instruments like GPI and SPHERE from the ground. But by accessing their full luminous range, this can give us access to their atmospheric chemistries, their compositions, and potentially some formation mechanisms. The second thing we really want to do is to complete the survey of exoplanetary systems at large separations. And I'm specifically thinking of lower mass planets at the widest separations. So let's go through these in a little bit of detail, and hopefully that will help you understand that this ERS program really took some major steps in addressing these two challenges, I think. So for the first goal, let's talk about this for a bit. As I said, we've mostly characterized planets from 1 to 2 microns, and for 3 to 5 microns outside this window, this is possible from the ground, but it's extremely challenging due to the modest sensitivity barrier that we face just due to the very high telluric background from the Earth's atmosphere. So here's a handful of some truly heroic efforts from friends of mine that have tried to image these planets at 3 to 5 microns, and I think you can see that the detections are challenging, to say the least. I think it's safe to say also that prior to this ERS program, there were no direct observations of exoplanets at wavelengths longer than 5 microns, full stop. So I also want to talk about the second goal that I listed. That has to do with completing the survey of exoplanetary systems at large separations. So here we see our demographic plot, mass versus separation with the transit and radial velocity objects close in. But then we can see this large smattering of directly imaged objects out here at wide separations, tens, hundreds of AUs. But I think what you can see is there's quite a floor here of sensitivity. We really haven't been able to detect anything less massive than about 2 Jupiter masses up until now. And really this lower right-hand corner of this parameter space is really unprobed. And we'd really like to understand the degree to which analogs of our own Saturn or our Neptune are present in this region of parameter space. And it's only JWST that's going to have access to this region of parameter space for the foreseeable future. So Talking about how the ERS program came about, I just want to say quickly that it was recognized by the JWST Advisory Committee. I know that some of you are in the room there. This committee was led by Garth Illingworth, and it was recognized there would be a very short window between when the first Cycle 1 data were obtained and when the Cycle 2 proposal deadline would happen. So this committee recommended 500 hours of director's discretionary time for the so-called early release science programs. So over 100 such proposals were submitted in 2017, and 13 successful proposals were selected. 2 of these were related to extrasolar planets, and the program I'm talking about today is the only one that really focuses on direct imaging. This is the high contrast imaging of exoplanets and exoplanetary systems. It's a 55-hour program. I'm the PI for this, but I really want to highlight the roles of 3 early career researchers that were really some of the driving forces in this community-led organization. Brittany Miles in Arizona, Aaron Carter, who's on his way now to Space Telescope, and Shrishmoy Ray, who's just finishing his PhD now with me. This was a broad, really inclusive consortium that spanned a lot of countries, a lot of career stages. So we're really proud of the consortium that we put together over many, many years. So what did we actually do? What did we actually observe with this program? Well, we focused on 3 targets. The first one is HIP 65426 that Liz first told you about. This is kind of a 7 to 9 Jupiter mass object at about 90 AU or so, and that means it's great for testing out the JWST coronagraphs. It's wide separation, it's bright. This was really a perfect object for us to characterize the performance of the JWST coronagraphs. So that was our primary coronagraphic exoplanet for study. Another object, another wide separation object, was VHS 1256b here. This has a separation of 8 arc seconds, meaning that it's perfect for doing direct spectroscopy with NIRSpec and MIRI. So this allowed us to get spectroscopy of a resolution of a few thousand, going all the way out to beyond 20 microns or so. We also observed a disk system, but I'm not going to focus on that in this talk, HD 141569. A lot of the work and analysis there is still ongoing. So there's lots more detail on the ERS program that we put together. It's in this paper here, and I'm showing these list of authors just really to highlight the huge number of people that have been contributing to this program over the past several years. It's a really awesome thing to be part of, and I'm incredibly proud of everybody involved. I think the biggest highlight from this program are really truly what are the first direct images of an exoplanet with JWST. This was a really amazing moment in August of 2022 when we got the first data. Here's a NIRCam image at 3.6 microns, and I say that it's a raw image, but really what it is, it's a coronographic image. So the coronographic mask is in place, but we still see a tremendous amount of this residual scattered starlight. So this is the systematic noise that we need to model, typically using observations of a reference star, and then we can then subtract this off to basically find the planet that's lying under this systematic noise. So we got a very, very strong detection across all NIRCam bands. For the MIRI case, we see a similar thing, but with a different morphology. So here's the residual scattered starlight pattern at 11 microns. And we're able to model this very well, again, using a reference star for observations, and we get a very, very strong, clear detection of the extrasolar planet. It might look like that this planet is very close to the host star, but keep in mind this is 90 AU here, and this just has to do with the resolution of JWST. So the subtraction of the residual scattered starlight noise, the PSF, if you will, really depended on the repeatability of the observations from the science target to the reference image. And that allowed this really excellent high fidelity detection of these planets to come through. To give you a sense for how well this coronographic subtraction is performing, I think Liz showed this basically detectability plot, where we're showing the sensitivity of these NIRCam observations now at 4.4 microns to a range of masses and separations. And I think the key takeaway here is that NIRCam is getting sensitive way down below a Jupiter mass here, really getting into that realm of exo-Saturns, exo-Neptunes potentially. So this is a total game changer. This is a totally new region of parameter space that we've never been in before, and it's really, really exciting. And like Liz said, it was this kind of result, this kind of performance that really motivated Aaron Carter's large medium program in Cycle 2, where he's actually going to be doing a survey of TW Hydra members to search for these analogs of our own ice giants. So to give you also a sense of the improved contrast, I just showed you the sensitivity a moment ago, but just for those of you that are coronagraph junkies in the audience, you might like to see these plots here. These are contrast plots showing the 5 sigma contrast versus separation in arc seconds, and we see the blue lines show the predicted performance of the coronagraphs for NIRCam and for MIRI on the right. The black lines are what we actually got, and the solid black lines are combining these post-processing techniques. So we can see that depending on the separation, there's really an improvement of a factor of a few at the very least. So JWST, the coronagraphs are really outperforming the predictions, and this was fantastic to see. Why are they really performing? What is it about the observatory? The reason, in my mind, is that the remarkable wavefront stability. Now, if Lee Feinberg is in the room, I really have to apologize to Lee because I stole this slide from him. I just got a screenshot of his slide at the Habitable Worlds meeting a few weeks ago. I was just flabbergasted by this slide, and I had to grab a screenshot. So, Lee, I apologize if you're in the audience. This is a plot of the wavefront, I guess, on July 3rd, and you can see the RMS is about 64 nanometers here. 2 days later, we have a very similar RMS of only just a little bit different number, but still in the vicinity of 64 nanometers, which is already great news. If we were to look at the difference of these two, we find something like this. Now, this is not a blank space in my slide. This is actually the difference in wavefront over something like 2 days. And Lee listed in his slide, and I want to make sure people didn't miss this, that there was a wavefront drift of 120 picometers per hour. So JWST is incredibly stable. The wavefront is incredibly stable, meaning that the observations are highly repeatable from the science observation to the reference observation. And this means that we can use a library of reference images throughout its lifetime. So this stability is really something to look forward to. But we're not just here to talk about coronagraphic performance. We're here to talk about photometry of exoplanets. And so our observations of Higgs 65426 really allowed us to get the first ever photometry of an exoplanet beyond 5 microns, shown here by these orange points here, and you can compare them to these old VLT points here as well. But really, what we'd like to do is spectroscopy on these objects. Those photometric points that I showed you a moment ago are great for getting a bolometric luminosity, maybe an effective temperature, etc. But let's do some spectroscopy. So for VHS 1256, the other wide separation object, we were able to get a full spectrum of this object using both NIRSpec and MIRI, and we were able to get a spectrum ranging from 1 micron all the way out beyond 15 microns. We see clear evidence for the usual suspects, carbon monoxide, methane, and water. But really what I'm excited about is if we look at these spectra in detail, here's the CO bandhead region around 4.5 microns here, showing just the exquisite detail in this spectrum compared to the predicted shape of this spectrum. So this high fidelity at these long wavelengths, covering a long wavelength range, really allows multiple spectroscopic features and a lot more precise abundances. So this is really exciting. It's really exciting also that we're seeing detections of silicates in these spectra here at about 9 microns. Silicates, what I mean by silicates are things like forsterite, perovskite. These are grains of sand blowing around in the atmospheres of these objects. These have been hypothesized, but this is a very, very clear detection. This is a fantastic discovery. Lastly, thanks, Susan. Lastly, as I finish up here, I just want to talk about maybe a fairly unknown mode of JWST. That's the aperture masking interferometry mode. In this mode, you take your photons from your $10 billion NASA flagship mission and you throw away 95% of them by covering up the pupil with an otherwise opaque mask that has a set of holes drilled into it, and this creates a series of interferometers, if you will. What this really does is it allows a new discovery space inside the inner working angles of the coronagraphs. And this was really a brainchild of Anand Shivaramakrishnan and lots of other people there at Space Telescope. So we're excited about that. There's a lot of other science-enabling products that I won't go into here, but I'll just list these saying that we have software post-processing pipelines available for coronography and aperture masking. We have simulation packages for coronography and for aperture masking. And there's a great J webinar led by Aaron Carter. So just to wrap up, the JWST coronagraphs are performing better than expected. The wavefront stability is better than expected, and this translates to excellent PSF subtraction. And the long wavelength coverage will really place powerful constraints on chemistries and compositions. So I'll leave it there and take any questions if there's any time.
Thank you. Thank you, Sasha. I think we have time for one question. Any online? I think everybody's just like tired after this long morning. The room is silent. I'm giving everybody a moment online to type their questions in. But if there are none. All right, well, let's thank Sasha one more time. Thanks again. That was an excellent talk. All right, everybody, on to our next talk by Niku Madhusudan.
Hello, everyone. First of all, I would like to thank everyone at Space Telescope and everyone who's contributed to making JWST happen. We are seeing the revolutionary impact it's having on exoplanet science, and by the end of the talk, you'll know what I mean. It's really game-changing, okay? And I would also like to thank our program support team here at Space Telescope who have helped us execute these very good observations, and you'll also see from the quality of the observations what I mean. And I thank my team here who have contributed various aspects of this project. So by the end of this talk, I'm going to use the first spectrum, broadband spectrum, and the first detection of carbon-bearing molecules that humanity has ever seen in the atmosphere of a habitable zone exoplanet. It's mind-blowing. Okay, I promise you that. So let's get started. Space. Wait. Nope. This is not working. The clicker doesn't work. Okay, good. So that's my outline of my talk. I'll just start with a brief motivation, talk about observations, how do we do the atmospheric retrievals and what it means. Big picture, why are we interested in this planet, K218b? The planet properties are here. The bottom line is that it's a small planet, a sub-Neptune, orbiting in the habitable zone of an M dwarf. Okay. So that should be interesting in its own right? So it orbits in a 33-day orbit, small transit depth relative to hot Jupiter is what we are used to. But this planet is about 8 times Earth mass, 2.5 times roughly Earth radius. The most interesting part of it is that its equilibrium temperature is similar to Earth. Basically, it receives almost the same level of insolation. So obviously, we want to understand what the atmosphere of this planet is like, what the interior of this planet is like, and can it host life, whether it's habitable, right? So people have done this. So exactly about 4 years ago, there were reports of a water vapor inference in this planet. This is order 60 hours of HST time, and we got this spectrum in the field. So there were several studies that reported, and there was an inference of water vapor based on that. So we did that too. We did atmospheric retrievals on this, and we came up with these posteriors. You can see there's a very clear water peak, or seemingly clear water peak. Methane peak, we called it a non-detection at that point. You can still see some the posterior leaking into the high abundance regime, but it was a non-detection. Ammonia was not detected. Very soon after, though, there were several studies claiming that the water inference was not robust for the obvious reason that it's degenerate with the methane abundance. So the abundance remained inconclusive, and there were other studies which said that actually the whole spectrum may not be real because it could be, we could be confusing it for effect of star spots. So those were the uncertainties we were stuck with ever since. Okay, so the atmospheric composition wasn't clear even after 60 hours of HST time. Some of you know that's a lot. As far the interior composition is concerned, so that's the mass and radius point in this diagram, and these are constant composition curves of pure iron, pure silicate, pure water, and so on. The radius of the planet was just above the water curve at the time. You can increase the temperature of the water; it goes slightly higher. But the point is, to explain the density or the mass and radius of this planet, you need a volatile envelope on top of the water layer. Okay, it can't be a rocky planet. You need a lot of water in it. You need a layer of hydrogen in it to explain the mass and radius. Obviously, there's a degeneracy, so any of these interiors are admissible. It could be a water world with a thin hydrogen-rich atmosphere. It could be a mini Neptune, like a smaller version of Neptune, still with a reasonable hydrogen atmosphere. It could be an entirely rocky planet, but with a large hydrogen atmosphere. So these are all admissible solutions. So again, we don't know what the interior is exactly. What we do know is that a small set of those solutions, so in this study, we explored that entire parameter space and found that actually there is a small region of that parameter space which does allow for liquid water on the surface of the planet if you have a thin enough hydrogen layer and you have a high enough albedo. So that was a ray of hope for us. So we started thinking, why don't we propose for JWST observations to settle what the atmospheric composition is, and that could in turn give us some constraints on its interior composition as well. Okay, so there we go. So we got time, order 20 hours with JWST to look at 3 transits of the planet, NIRISS, NIRSPEC, and MIRI, all the way from close to 1 micron to 10 microns, and get a full spectrum and see what we get. So far in this work that I'm going to present, we observed only 2 transits, one with the NIRSPEC G395H between 2.7 to 5.2 micron that was observed in January this year, and then another up to 2.8 micron that was observed very recently in June. These observations were all standard time series transit observations. The data reduction procedures were all pretty standard, no surprises anywhere, so I'm not going to bore you with the details. I'm just going to show you what the spectrum looked like on this on the detector, and then the light curve is spectacular. The error, the noise we get, the residuals are order 100 ppm, and when we propagate the errors and expect theoretically the errors we are getting on the transit depth, the precision is comparable to our theoretical expectations. So nothing dramatic whatsoever. Same with NIRISS. NIRISS, as some of you may know, is a bit more challenging because it's a slitless spectrograph, so there is a lot of background. So we do all the usual corrections. And again, the light curve looks great. The noise profile is also pretty good. In the longer wavelength, we are seeing a bit more noise than expected, but all NIRISS observations are seeing that. So no surprises there. We do see a small star spot crossing event. So we actually model the star with the spots and the transit all at once to account for that, so on and so forth. So with all that, you probably are looking for what the spectrum is, right? So there we go. So that was our HST observations with 8 transits, order 60 hours. And let's see what we have with JWST. Should come up. There you go. How's that? Say, wow. Yes. Right? So that's with just 2 transits, 14 hours with JWST. Look at that. From 1 to 5 micron, you can count. I promise you there are 5 peaks of one molecule here. Okay? And that's HST that we had. So when I talk about a phenomenal shift that this is going to cause, this is what I'm talking about. Right? Huge. The impact is huge. And this is a habitable zone planet we are talking about. So before you get too complacent with this figure, let me take you further. So what that spectrum means, what does that spectrum actually mean? What does it tell us, right? So what we do is atmospheric retrievals. What it is you have the data. It's basically a model fitting exercise. You have a parametric atmospheric model, and we do a Bayesian parameter estimation to extract the atmospheric properties of that model. What are the atmospheric properties for a canonical model? There are 11 nominal molecules that we expect in this sort of atmospheres. We have the pressure temperature profile, clouds and hazes, and so on. Plus, we have a wide range of other considerations like stellar heterogeneities, scattering from multiple molecules, shifts between the detectors. We are seeing that those can also happen. All of these things we are doing. And so let me get to the punchline for the results. So these are actually the chemical abundances that are coming out of that spectrum that you just saw. Okay. So you can see this very sharply peaked methane detection. Believe it or not, this is the first time methane has ever been detected in a temperate exoplanet, period. This solves what is known as the long-standing missing methane problem we have been trying to solve for the last decade or more. Okay. This is the first detection of carbon dioxide in a small planet, period, ever, outside the solar system. Okay. This is at 5 sigma, this is at 3 sigma. And hold on to your chairs. We don't know if this is real yet, but DMS is a biomarker. So on Earth, dimethyl sulfide is produced just by life. You cannot produce it any other way. So we are not claiming this as a robust detection. That detection actually goes away if we massage the data in different ways. We move this, introduce enough offsets, it can go away. But you still see the posteriors are not totally non-detections like this. There are still peaks. So there is something there we don't know. So we are calling it tentative. But folks, if in a few years, if we realize that this is actually DMS, history is being made as we speak right now. I kid you not, it's actually true, right? So with that, those are our nominal, these are our very robust detections. This is a nominal inference, and then we actually don't detect water vapor. We don't detect ammonia, and then there are some other species which we also don't detect, but their upper limits are interesting. So for those who are interested in what these estimates are like, these are the estimates. You can see here we're introducing different levels of offset. So if we go to 2 offsets, we can actually lose our DMS feature, but otherwise these abundances are consistent between the numerous retrievals we have run. Bottom line is that there's a humongous amount of methane in this planet, 1% by volume, 1% by volume of CO2. Never, ever seen in a planet elsewhere. Okay, so that is the summary of the atmospheric composition. It is a hydrogen-rich atmosphere with a lot of methane and CO2, non-detections of various important molecules, water, methane, ammonia, carbon monoxide, and so on, and marginal evidence of a potential biomarker, but the jury is out on that. And then there are evidence for clouds and so on that are also important. Now, let me tell you what this abundance, what this composition actually means. Now, I told you how there's a degeneracy in the interior composition. Turns out if you do a chemical calculation and you have a deep hydrogen-rich atmosphere, it sets into equilibrium very quickly if you go into the deep atmosphere. So molecules like methane and ammonia are expected in cold atmospheres as we see in the solar system. But if you remove them by photochemistry or something, in the deep atmosphere, you still attain equilibrium and it will be replenished very quickly. Okay, so you cannot get rid of CH4 or ammonia if you have a deep H2-rich atmosphere like the solar system giant planets. So long story short, the only way we can explain the abundances we are seeing is if you have a surface in the planet that cuts the recycling of those species. Moreover, that surface has to be a liquid or some water surface. It can't be just a solid surface, the trends that we are seeing. And there is numerous papers written on this in the literature over the last couple of years, but the summary is that you need a water surface. Now, that brings us to the whole motivation that we discussed in the abstract, which is that this is exactly what we predicted 3 years ago. So this is a triumph of theory and observation going hand in hand. This is what we predicted and used K218b as a prototype for what we coined as a Haitian world, a planet with ocean-covered surface and hydrogen-rich atmospheres, and we predicted that K218b should be a good target for that. I won't have time to go into this, but Haitian worlds are basically planets that can have a large amount of water and thin hydrogen atmospheres, and those expand and accelerate our search for life by just expanding the habitable zone enormously. You should read that paper if you're interested in. So these are my conclusions. So if I came here and I told you we just detected methane in this planet, that would already be a revolution in the field because we have been looking at it for that for like a decade. And here I am telling you that that's only one of 3 bullet points in my talk. Okay, so we have sort of addressed the missing methane problem, and then the robust detections of methane and CO2 together most likely is the first evidence for the presence of an ocean on an exoplanet. It's huge again, but again, I still call it a possible. I'm not saying it definite. We need more observations to just robustly confirm that. And finally, there is a potential inference of a possible biomarker. Let's hope that that goes away with more data, because that is a scary prospect. Right? So if we need more modeling, more data for robustly identifying that, we need more theoretical work to establish if that DMS is actually unique to life on that planet. It definitely is on Earth. Okay? So we as a species are trying to make these major advancements, and if this is proven, this will be huge. But we as a species also need to be extremely responsible and make sure that this is indeed a robust statement to make. So I'm happy for that to go away tomorrow. But if it doesn't, then folks, you're hearing it for the first time here. Thank you.
Great, thank you all. Are there any questions in the room?
Hi, Madhu. Jacob Bean, University of Chicago. Really exciting. I have to ask the question, in the ERS program, we've seen in a really high signal-to-noise spectrum that has a lot of water bumps, similar to a lot of methane bumps, but at higher signal-to-noise than this, there are a lot of degeneracies and problems with free retrievals. Can you talk about what sort of problems you might face here that more data will help you sort out?
Yeah, that's a very good question. So just for completeness, I'll tell you the number of models explored in this work are hundreds of millions of model evaluations. So tons of robustness checks just to address that degeneracy problem. So methane, for example, so we're actually, our litmus test for robustness is that I don't have to run a retrieval to tell what molecule is there. I should be able to see it by eye. So those peaks, there are 5 methane peaks there in that spectrum, at least 5 methane peaks. So that is undisputable. CO2 is a 3 sigma. I would call that, by an extreme robustness standpoint, a borderline case. But even that has a couple of peaks, and we detect it it just doesn't go away. DMS is what I would call it as a weak inference, because we try to kill the signal in every way possible, right? So if we take the data at face value, we do get between 2 to 3 sigma, but then we try to introduce all kinds of possible offsets and made it go away. Yet you still see the peak. So that is where I would leave it. New data, in my view, would only help in increasing the robustness, like the detection significance. I'm not sure. I don't think that it'll get rid of CH4 and CO2, but I think it'll increase the detection significance a lot. DMS, it may make it go away or increase its detection significance. The jury is out on that.
Okay, I saw there was a conversation online. Is that questions or?
There is some conversation online. Logan Albert asked,
a short question I can do in between.
how will MIRI observations help? And there is an answer online, but if you want to answer.
Yeah. So we do have another transit coming up on MIRI, and MIRI actually has a huge DMS peak. So huge. So that should give us a very good constraint on DMS. Jennifer has a question.
As long as it's really short, we need to move on.
Really short, but the answer might not be. This is
That's not my problem.
fabulous. Are there any laboratory astro work on DMS to see if there are, astrobiological conditions under which it might be produced or not? Yeah.
There are some studies that have been done. DMS you can produce from life. That's there. I think in
space conditions. I was
that
wondering.
I'm not sure. But I will say that lab experiments are really needed to establish the line lists of DMS, which are not very well known. So we're using very few line lists that are, cross sections from Earth-based experiments. Thank you.
We better move on. Let's give Nika one more round of applause.
If they can hear me, they can't hear me.
All right. Up next, we have.
Testing.
Up next, we have Jacob Beam. Go ahead.
I think the only way to follow that talk is by showing more spectra of transiting exoplanets. All right. So I'm going to present results from a GTO program. This is a GTO program that's been carried out under JWST Interdisciplinary Scientist Program led by Jonathan Lenine. My team at the University of Chicago has been leading the exoplanet component of this program. And, you know, you can see from Madhu's talk previously the power of JWST over what we had previously. And so this is a similar slide that he showed, but now looking at the thermal emission of a transiting planet. Before, with WFC3 and Hubble, we basically had access to one spectral feature from water. We had some spectrophotometry points that allowed us to say something about the carbon-bearing species, but we had no spectroscopy longward of about 1.7 micron that could really allow us to see the chemical compositions of these planets' atmospheres. When you just have one spectral feature due to water, you can try to put an abundance constraint on the water and use that as a proxy for the metallicity. You can put an upper limit on the C-to-O ratio, but you really can't reveal the full interesting chemistry of planetary atmospheres. So we've been strongly limited by wavelength coverage, spectral resolution, and data quality leading up to this in terms of characterizing transiting exoplanets. Now, ground-based high-res has made some inroads into this problem, particularly by allowing the detection of carbon-based species like CO. But it's a question, that's a very tricky technique. I won't go into the details, but the question is whether those are reliable and whether you can actually get good inferences from that. In our GTO program, we've been focused on giant planets, and we're trying to take giant planet characterization from just detailed studies of individual objects to start branching out and make comparative studies between the planets. That's sort of our secret sauce of this program. Now, our targets are kind of a grab bag of targets. We have 5 giant planets and 1 rocky planet. The rocky planet I won't really talk about. But the giant planets were selected to be really high signal to noise, to really be canonical objects, and also to enable comparative studies, as you'll see. We've focused our spectroscopy on the 3 to 5 micron range. We've used a combination of NIRCam and NIRSpec to probe that region. That's where you can see both carbon and oxygen-bearing species to try to make a measurement of the metallicity of the atmosphere traced by these important volatiles, and also to measure the C-to-O ratio. So I'm going to start by showing spectra from 2 of these objects that were both observed around secondary eclipse, where we measure the thermal emission spectra of the planets. I'm going to go through these kind of quick just to move along. This is planet-to-star flux ratio measured at secondary eclipse as a function of wavelength. This is one of the planets, HD 149026b. These are NIRCam observations where you see a clear CO2 feature, and there's also a water feature here. These models, we have a best fit model, and we just take out the opacity of different species to highlight what's sculpting the spectrum. So this is also a spectrum of another hot Jupiter, WASP-77, capital A, small b. This is a really precise thermal emission spectrum, signal to noise of 15 to 40, a spectral resolution of R of 250. And so you can see overplotted in this the Spitzer points that we had before. We have basically similar level of precision on these Spitzer points, but now we're doing it at, you know, moderate resolution spectroscopy over this wavelength range. Here you notice an absence of CO2 and then also strong absorption from water. So we published papers about these 2 individual objects before, but the really exciting thing was being able to compare these objects. Now, if you just take the secondary eclipse spectrum, the planet-to-star flux ratio, you can't really compare objects and really see differences and similarities between them. But if you convert to the old planetary science standby of the brightness temperature, you find that these planets are actually quite similar. They have very similar temperatures. So the brightness temperature is just taking the measured planet-to-star flux ratio, multiplying by the spectrum of the star, and then converting the planet flux into the equivalent blackbody temperature for each of your spectral points. So here we can see those 2 spectra now of those objects plotted on top of each other, and we can see really distinct differences. We see that the CO2 feature that's measured for HD 149026b is not detected in WASP-77, whereas they seem to show a similar level of water absorption. So this agreement here suggests that the thermal structure of the atmosphere is similar and the amount of water is the same, but the overall difference is the metallicity of the atmosphere as traced by the C-to-O feature strength. So the key result is these 2 giant planets, which otherwise you would expect to be fairly similar, actually have very different metallicities, very different compositions. Now, how do we understand these differences? Well, one hint to understanding these differences is that, well, one of these planets is actually a little bit different than a lot of other transiting planets. HD 149026 is a transiting planet that we've known of for a while, and we know it's actually very metal rich. We know that because the planet is a little bit more massive than Saturn. It receives more than 100,000 times more radiation than Saturn, but it's smaller than Saturn. So that means its heavy element abundance is about 66% by mass. So this is a very metal rich, very metal enhanced gas giant type planet. So our result is that the metallicity of the atmosphere is similarly enhanced, 50 to 200 times solar metallicity to be specific. And that actually traces the expectation for the internal bulk metal enhancement of this planet. WST 77 is a more prototypical giant planet with a mass and radius comparable to a lot of other planets that we know of. The interesting thing about this result is that it actually demonstrates that high-resolution spectroscopy from the ground is delivering reliable results, at least in this case. We find a subsolar metallicity for this planet's atmosphere. That's a bit challenging to understand because of the core accretion model of planet formation suggests that you should have metal enhancement in the planet's atmospheres due to the accretion of planetesimals while the atmosphere is collapsing and forming, but we get this subsolar metallicity. It does agree very well with a high-res result, prominent high-resolution result from a couple of years ago, but it actually disagrees a little bit with HST spectra. One of the surprising things that I've seen in the first year of JWST has been the agreement with the Spitzer photometry and the somewhat tension with the WFC3 data. You can see here the forward model from high-res shown in gray, predicting very well what we expected, what we actually saw with JWST. So that suggests that looking forward, we can combine JWST with ground-based high-res in these cases and really get more detailed information about the planets. Moving on to another planet, the most famous transiting planet, perhaps HD 209458b, the first transiting planet that was discovered. In this case, we measured the transmission spectrum of the planet, and this is what it looks like. In transmission spectroscopy, absorption is up, so we're seeing absorption of CO2 and water. So we detect CO2, water, and also patchy clouds in this planet. But where are the other molecules? There were quite a lot of studies over the last couple of years looking at previous data that suggested the existence of a wide range of molecules in the planet atmospheres that we're not seeing. One of the most prominent was, again, a ground-based high-res result suggesting the presence of 5 carbon and nitrogen-bearing species in addition to water. These are the cross-correlation maps for those detections and a non-detection for CO2. We are consistent just on the surface with the detection of water, detection of CO. We don't see CO in our spectrum, but it's buried under CO2. They didn't see CO2, and we do, but that's probably also explainable by their lack of sensitivity to it. But they detected this whole host of other molecules, methane, as Madhu mentioned, the missing methane problem we're worried about, ammonia, C2H2, and HCN. The question is, where are those molecules, and would they have shown up? This is a busy plot, and I just want to draw your attention to the green line. This is what you would expect if you injected the methane abundance predicted by ground-based high-res into our data. You can see by eye it's clearly very inconsistent with our data. Like Madhu, we're performing retrievals where we try to put limits on the abundances of these species. We perform a chemical equilibrium retrieval where we let these 4 species that we would expect to see in our spectral range, since they're trace, be free and independent of the equilibrium. And we find their retrieved abundances, shown by the posteriors, are consistent with the expectations of equilibrium. So we're not finding evidence for out of equilibrium, but it's also strongly inconsistent with what you expect from ground-based high-res, in particular for methane, C2H2, and HCN. The high-res results suggest much more, orders of magnitude more abundance of these chemical species than we actually see. These results have been cross-checked by Luis Wellbanks with an independent retrieval, so we think this is pretty robust. So we're not really sure what to make of this tension. The only thing I can note is that the previous high-res results did not perform a retrieval, so these are abundances they predict that give the best cross-correlation signal in their data, but we don't see those. And so I think a joint study of these JWST data and those high-res data are needed to really identify whether those molecules are present just at lower abundances than they originally said. Okay, back to our idea of comparing planets. We're now comparing HD 209458b with WST 39b, which was targeted extensively in the ERS program. What we do is we can normalize these transmission spectra by the scale heights of the planet's atmospheres and the size of the stars that they orbit to put the transmission spectra on a similar scale. So that's what we've done here. You can see here the spectra, again, agree overall, but show some differences that are quite interesting. In particular, WST-39 shows stronger CO2 absorption and weaker H2O absorption. We think this is a clear marker of the carbon-to-oxygen ratio in the planet's atmospheres. If you calculate models where you predict the abundance ratio of water to CO2, you see that it tracks the C/O ratio very well. Those two lines are offset just because there are slight metallicity differences between the planet's atmospheres. So just from looking at this spectrum and knowing how water and CO2 change with C/O ratio, you can read off that these planets have very different carbon-to-oxygen ratios. Our retrieved C/O ratio is very low for HD 209458b, 0.02 to 0.15 at 1 sigma. That's sensitive to model assumptions, and so I don't know if we can hang our hat on the exact value, but what we can say for sure is that HD 209458b has a much lower C/O ratio than WST-39. So what we're seeing is clear diversity in atmospheric compositions between these planets. Finally, one of the things that we've been trying to do over the last few years is do population studies of giant planet atmospheres and see if we can detect some of the trends that we expect from the solar system. A couple of these trends are how atmospheric metallicity corresponds to planet mass and also bulk metal fraction. You can see there are clear trends in for the solar system giant planets. And the question is, now that we're measuring carbon and oxygen abundances in the atmospheres of giant exoplanets, do they follow this same trend? And so this is what we have right now. The data show an intrinsic scatter that is, I think, really clear and robust now. So there's hints of a trend in both of these plots, but there's also a lot more scatter than we expect. In the mass metallicity relationship, HD 149 is so metal rich, WST-77 is so metal poor, suggesting a very large diversity in compositions. The atmospheric metallicity versus bulk metal fraction is a little more tight, but again, this low metallicity for WST-77, which really seems robust, is challenging to accommodate in this simple statistical trend. Okay, so what does this mean looking forward? I've said this word diversity like 100 times now. Diversity of giant planet atmospheres. These giant exoplanets have different compositions. What we're trying to do is we're using the atmospheric composition to trace planet formation and evolution, but we can't just do that with a handful of objects. We're going to need a large statistical survey to take advantage of this opportunity. Ground-based high-res has access to some of the things that we're doing with JWST, but it's still a very tricky technique. 2 of the 3 cases that I've seen a comparison between high-res and JWST have agreed. 1 is not. So I think that we still need to try to understand that. And I didn't have a chance to talk about this because the results are too new, but we're actually getting really exciting results for M-dwarf rocky planets. It could be that the results that you're seeing for TRAPPIST-1b are not representative of the broader population of rocky planets around M-dwarfs. We're going to need more planets to really dig into this, and I hope to be able to present those results in a few months. Thanks, and I'd be happy to take questions.
All right, do you have any questions in the room?
Madhu, it's only fair that you asked me a question, I asked you a question. Is he still here? Come on. Come on.
Any online? Okay, online. Oh, no.
Gotta wait. Patience is a virtue.
So I'm trying to understand the scatter plot for the metallicities. We were hoping to get some nice mass metallicity relation, but with that kind of plot, what do you think is a fundamental physical process that we could potentially be constraining for giant planets?
Do you mean, well, what I can say is, the idea of this plot is what is the competition between gas accretion and solid accretion during the formation of a giant planet's atmosphere? I don't think this spread is inconsistent with what we see in, say, the mass radius diagram for transiting exoplanets, and I think we're now mapping the metallicity to the bulk composition, and we see there's just an intrinsically a large spread in that. I think there's probably a trend underlying this, and that we need at least an order of magnitude more objects to simultaneously measure the slope and the dispersion. It's a cosmic variance problem. There's an intrinsic dispersion in these objects, but fundamental underlying trends that require statistical sample to reveal.
Okay, I think we better move on. Let's thank Jacob again. Right, our last speaker is, oh gosh, it is Elin Hawk. Sorry.
Thank you. Can everyone hear me okay? Is the mic working? Okay, awesome. All right, I'm going to try and get through this as quick as possible because I know I'm the last talk of the day. So thank you all for sticking around. So I'm going to talk to you about direct imaging spectroscopy of substellar companions of JWST and highlight our process to obtain high contrast spectra using the NearSpec IFU shown here. So we've seen this plot many times so far. There are many methods to detect exoplanets. So we have the transit method, which is in purple, microlensing in gray, radial velocity in gold, and direct imaging in blue. So again, this is a plot of mass versus semi-major axis for all the different planet detection techniques. So each technique is sensitive to a very specific population of exoplanets. Another feature on this plot is that everything in bold or with an outline is an object with spectral information. So essentially, only the transiting method and the direct imaging method can give us spectral information, which can tell us about their atmospheres and how they might have formed. So if we do direct imaging spectroscopy with JWST, we'll be able to extend our spectral coverage past 3 microns. But JWST will also try to expand the region of direct imaging spectroscopy to fainter and lower mass planets. So shown in the plot now, we have red stars that represent exoplanets that will be imaged with NearSpec or MIRI in JWST cycle 1 and cycle 2, showing that we are already starting this process. But if we want to continue to expand the gap between transit and direct imaging, we need to push for as small separations as possible, so we need to get good at high contrast. So for direct imaging, moderate resolution spectroscopy from the ground has shed light on chemistry of these substellar atmospheres. Shown to the left is a plot from Konopecki et al. 2013, showing HRite 799c with spectral templates for various molecules detected in its atmosphere. But this wavelength range doesn't go past 3 microns. Shown to the right are some of the best spectra past 3 microns from the ground of HRite 799c, D, and E, and they are much lower resolution, making it harder to identify individual molecular features. So we get to see this plot again because it's so exciting. JWST NearSpec opens the door to moderate resolution spectroscopy beyond 3 microns. So here's our plot of VHS 1256b from Miles et al. 2023, illustrating the amazing spectral features and spectral information we've never had access to before. But VHS 1256b is a fairly low contrast object to image due to its large separation. So if we want to do high contrast imaging at close separations to their host stars, we need to develop optimized data processing to do so with NearSpec and MIRI, because these instruments weren't designed for high contrast imaging of exoplanets. So focusing in on NearSpec specifically for this talk, it's spatially undersampled and is especially early in the mission, so some calibration and pipeline optimization processes are still ongoing. So how can we use an IFU that's spatially undersampled to obtain high contrast, moderate resolution spectra? So I'm going to talk about our GTO program, PI'd by Marshall Perrin. So we wanted to answer this question. So knowing the challenges ahead, such as instruments designed to look at faint puffy galaxies, IFU spatial undersampling, and new pipeline calibrations and algorithms, and again, we're still early in mission, it's year 2, or beginning year 2, we've developed a program to try and mitigate these issues. So we wanted a program to test various ground-based techniques and strategies for high contrast imaging. We wanted to work directly on detector images, avoiding pipeline interpolations, and to test and refine these methods with a moderately challenging target. So we chose the substellar companion HD 19467b. It has a moderate contrast in the near infrared by about 10 to the -4 and is at a moderate separation at about 1.6 arc seconds. This object is a cold, old brown dwarf orbiting a solar-type star. The advantage here is that this object has a mass that is dynamically measured. So this is independent from atmospheric modeling. This makes it a candidate to test substellar evolutionary models, as well as high contrast imaging with JWST. The object was also looked at with JWST NearCam, with images at 4 filters from Greenbaum et al. 2023 shown on this slide. So here's our first data of HD 19467b using the NearSpec IFU. So when using the pipeline, the data are assembled into an XY lambda data cube. So portrayed here. So we have one slice to our left, and then we're moving through the wavelength axis of the data cube in our video to the right. So the companion should be where the blue circle is, but our data cube doesn't really show that it's there. It's really, really buried underneath of the stellar light. So to create the data cubes I showed on the previous slide, JWST pipeline uses a 3D drizzle technique that's used with the slicer type IFUs on board JWST. So MURI MRS and the NearSpec IFU. So Law et al. 2023 shows that there are systematic oscillations in the spaxels. So with a combination of dithering and averaging over the spaxels in our data, you're able to mitigate some of these wiggles and oscillations. But for high contrast imaging, if we want to conduct PSF subtraction per spaxel to get rid of the starlight, even 1% of systematics is insufficient, and averaging over multiple spaxels are not options when we're looking at tiny planets. So to mitigate building data cubes, we've looked at the 2D detector images. Because NearSpec is a slicer IFU, we can look at the individual slices. So shown to the left are the calibrated 2D detector images for detector 2 on NearSpec. Highlighted in the red region is where the companion should be. So if we zoom in, we can see the spectral traces of the companion, highlighted in red, and the spectral traces of the starlight. So these traces can actually be forward modeled to disentangle them from one another to pull out the signal that's just coming from the companion. After applying this method, we actually get a very strong detection of the brown dwarf companion. So shown here is the median spectral cube image from JWST calibration pipeline. To the right is a detection map representing the companion signal to noise ratio at each of the sky coordinates. The signal to noise was calculated using a joint forward model of the companion and the host starlight. And so the signal to noise for this companion is 249. For more information on this framework, please see the poster by J.B. Rufio tomorrow morning. Here's his photo if you see him around. Say hi, tell him I sent you. All right, so here's where we were in 2020. So this is all the spectral information we had on HD 19467b. This is what we got with NearCam. And this is what we got with NearSpec. So that's a whole bunch of spectral information we never thought we'd be able to see. So focusing in on the spectrum, we have detections of water, methane, CO2, and CO all in one go. One of the hardest challenges we are facing is modeling both the CO2 feature at 4.2 microns and the methane feature at 3.3 microns. Vertical mixing parameterized by KZZ is included in our fits. So the models shown here are actually Phoenix custom models. The top panel shows the best fit for the entire spectrum, noting that the model actually fits detector 2 data a little bit better than detector 1. When we fit the 2 detectors separately, we can actually see that the methane feature really wants a lower KZZ value, and the CO2 feature wants a higher KZZ value, shown with these 2 bottom panels. So there's some interplay between CO2 and methane in vertical mixing and in non-equilibrium chemistry. So we need more knowledge of non-equilibrium chemistry with these objects and with substellar objects in general. So these are also just preliminary results, and we also plan to constrain molecular abundances next. So other JWST Cycle 1 and Cycle 2 programs aim to use NearSpec and MURI to obtain spectral information of substellar companions. So here I'm going to show one example. So I'm the PI of the Cycle 1 program to image the WISIS-1 system. So we targeted these 2 Jovian exoplanets, WISIS-1b and c, shown in the plot to the left from Bond et al. 2020. And we did get 1 to 12 low resolution spectra of the objects and moderate resolution spectra from 3 to 5 microns. So what's interesting about this system is that it's a multi-planet system. So if we want to do some comparisons, it's much easier to compare planets that are in the same system rather than planets that are in different systems. What's also interesting is that WST 1c is about 6 Jupiter masses. It's much farther separated than WST 1b, which is 14 Jupiter masses as in closer to the star. Shown to our right are actual near-spec IFU data of the two objects. So you can see that we actually were able to get both of them in the same field of view. So the only caveat here is that C is kind of on the edge of the detector in 2 of our dithers, but we're going to try and mitigate that using the framework I mentioned earlier. So I'm going to focus on WST 1c for now. It's farther away from the star. There's less contaminated starlight. So here's the data that we have from the ground. Here's our near-spec prism data, the low-resolution data. And then here's our MIRI LRS data, going all the way out to 11 microns. And then this is also the first detection of silicate clouds in an exoplanet around a sun-like star. So we saw something very similar at BHS 1256b, but this object is 6 Jupiter masses. So it is much lower mass, very, very interesting, and it is around a solar-type star. The system is also quite young. And I'll finish off with some conclusions. So some takeaways from our work. NIRSpec works extremely well for high contrast imaging spectroscopy. Shown to the right are contrast curves from our framework using NIRSpec plotted against the NIRCam contrast curve from Carter et al. 2023. So there are also, these are just 2 programs of a huge subset of many JWST programs to get direct spectra of substellar companions. NIRSpec now enables moderate resolution spectroscopy from 3 to 5 microns of known exoplanets and will push into new territory with cooler sub-Jupiter worlds at smaller separations. Thank you.
Thank you. Do we have any questions? Right.
Hi, thank you for your talk. That was very interesting. I was wondering, I'm not sure if you can answer this question or if I should visit the poster tomorrow. I was just confused about how it works. So are you just doing a PSF subtraction on the detector, or what's the...
It is a very complicated framework.
Okay.
So we're essentially forward modeling the modulations of the speckle light on the 2D detector images, and we're subtracting out, we're also forward modeling what the companion would look like on the 2D detector images. We also are doing reference differential imaging in the point cloud as well. But yeah, you can talk to JB Rufio for more detail on this framework. I could give it like a 30-minute conversation about this, about this framework. I only showed just the tip of the iceberg here.
Okay, I will find him then.
Yeah, yeah.
Thank you.
Maybe a conversation for earlier in the day. Any other questions in the room? Oh, here we go. One more.
Hey, great talk. I was wondering what the best wavelength resolution across the whole spectrum you're able to recover for MIRI would be. Like, would it, in terms of like the number of angstroms you would get per bin, per wavelength bin?
Could you say that question again?
So for NIRSpec, like you can get down to about 40 angstroms or so per wavelength resolution element, which is good enough to start pulling out a little bit of line emission. And I was curious what the best that could be done with this technique would be.
Yeah, so that's a difficult question. We've only really done this technique on one data set. So this is the first time we've also saturated the NIRSpec IFU. So we were playing around with some really wild data. So for this data set, this method works really, really well. This resolution is high enough that we can actually see the molecular lines. So if I go back to this slide real quick, so if you see those red rectangles, those are the CO lines that you see in the spectrum. So we can actually see that on the detector here. So we have the resolution to actually be able to disentangle that and look for the actual features. But as we go into like higher contrast, that might change, but we're hoping that it doesn't. I hope I answered your question. Oh.
I'll just chime in to help out a bit. The LRS data, we're showing here the MIRI data is LRS. For MIRI, we have not tried this yet at high resolution, high contrast. Polychronos Potapus is Polychronos here? He's supposed to be here this week. Tomorrow, arriving tomorrow. Talk to Polychronus tomorrow.
Yes.
For Miri.
Yeah, for Miri, MRS, exoplanet stuff, Polychronus is your person. 100%. Here's back. You got me and JD.
Okay, one last quick question here.
Hi, nice talk. Sandy Leggett, Gemini, Hilo, Hawaii, over there. I think I can help you with the models, with the methane, and that 3-micron methane has been a long-standing problem.
Yeah.
But I've been trying some different models, so I'd like to talk to you. Maybe I can help you out.
Ooh, yeah. Thank you.
That's effectively a brown dwarf. I mean, it is a brown dwarf, but the 900, the 900 Kelvin, 4.5.
Yep.
So
T4.5 or 5.5.
Yeah. So I can help you out with those models. You can talk tomorrow.
All right, let's give Keelan one more round of applause. And thank you all for joining us for Exoplanets this afternoon. We'll pick it up again tomorrow. Chris, are you here? Do you need any announcements? I don't see anybody, so you're free. Go.